This presentation is for the LAS 2022 Symposium on the project TLeaves, or Transfer Learning for Recommender Systems. To introduce the problem, we have a large data set and logs of how analysts interact with these data. We are studying how to use these logs to predict which organizations or groups of organizations are interested in which data, with the goal being to recommend data to the analysts. We believe that this will allow us to benefit the analysts greatly by providing them with high-value data, as well as retain more important data for longer. Some constraints on this work include that the dataset is prohibitively large, which makes the application of methods and iteration both difficult and time-consuming. The data and analyst behavior also changes with time, meaning that any model that we create will need to be able to adapt to the changing data that underlies it. This work began in 2021 with RADS, or Recommender-Based Analyst Data Decisions, which focused on approaching the problem by using the methods and tools developed for recommender systems in e-commerce and applying them to our project on the high side. So to go into some detail to what we did here, the table below shows the type of correspondence we made between low-side e-commerce data and our data that was internal. So an online shopper would correspond to an agency analyst. The level of interest of an online shopper would be to view it, to cart an item, or to buy it. And this would correspond to a simple query, a more in-depth view, or the highest level, which would be to add the data to a report. The property of a user would be their ID or their session, whereas this would be which organization an analyst belongs to. And there are many classified categorical values in the problem domain, which we would correspond to just the various properties of the products in e-commerce. We use tabular learning methods, including but not limited to XGBoost and TabNet, to evaluate how well the dataset could be used to predict which organizations were interested in which data, and we evaluated these models using the confusion matrices and Matthews correlation coefficient, which I will describe in greater detail later. In TLeaves, we use these models to train on past data and make predictions on future data. So to give some outcomes from RADS, we identified a low-side e-commerce dataset which shared many high-level features with the high-side data, which made it an effective proxy for our internal dataset. We were successful in adapting these methods to the internal data. However, limits to our processing and data storage capability restricted the scale of our experiments, which brought us into TLeaves in 2022. In TLeaves, we scaled these methods up and applied them to the time domain as well. We found that the models were often successful in making predictions using the past data with Matthews correlation coefficient scores that were often above 90 or even 99%. These models also provided feedback in the form of feature importance, which informed us as to which aspects of the data were determining which people were interested in which data and why. Here I show results of a model which worked well on past data but did not work well on future data to show the importance of these different evaluation metrics. So on the right, I show two matrices, the top one being the training of the model on past data. So we can see here that the model had many true positives and true negatives and is doing a good job of categorizing the data with only a small number of false negatives and false positives. You can see that the accuracy score and MCC are both very high. However, moving to the future data, which is the matrix below, we can see that there are many more false positives and false negatives, and the model is not doing a very good job. However, because the data is so imbalanced, we're only trying to pick out a few thousand entries out of millions. The accuracy score is still very high, because even if you just predict false for every single entry, you'll be very, very close to 100%. This is why we use the Matthews correlation coefficient, because it essentially represents the correlation between the predicted and true outcome of your model. So the model is not doing a good job, and we see that the MCC score is very low. However, our model often had an MCC above 0.9 or even 0.99. Now, to go into feature importance, here I plot a breakdown of the feature importance for two models run on e-commerce data. For the first run, a single feature, F4, was enough to predict which products a customer was interested in, while for the second run, we needed three features, F5, F6, and F7. On internal data, this kind of plot helps us understand why different organizations are interested in the data that they query, and whether we expect these predictions of the model to remain accurate as time passes. Looking into the future, Our work in 2023 will continue in a project called ORBS, or Operationalizing Recommender-Based SIGINT. Our focus will be taking what we've learned in RADS and TLeaves and bringing it to the analysts themselves. Challenges will include applying our methods, which were limited to queried data, to the full data repository, and working with analysts to determine what their needs are and what they can gain from being recommended high-value data, and finally, what they can provide to help tailor their results. Any further questions can be redirected to myself, Blake Hartley, or Stephen Williamson, my LAS contact. Thank you.